Yeah, it's a pleasure to have Li Fu, who will speak on the Generalized Franchetta conjecture. Now, looking forward to the talk.
Thank you. Thanks for the invitation. I'm really happy to speak in this derived seminar. I'm actually a faithful follower, but only after the sessions usually. Okay, I will talk about some joint work with Robert Laterveer. And then probably if I have time, I will also speak some work joint together with Robert and Charles Vial. Okay. Oh. So I will start with a classical question asked by Franchetta. The so-called original Franchetta conjecture, sorry. Sure. In 1954. So if I fix integer g at least 2, let me denote by mg the moduli stack of genus-g curve. G curves, smooth curves. And let me denote by c the universal curve. So mg1, the universal curve. This is the natural morphism pi. Then the conjecture was that the relative Picard of this projection is cyclic. So pi upper star of the Picard of mg is actually generated by the relative canonical bundle. Okay, equivalently, we could say this very explicit in a very explicit way. So for any line bundle L on C, the universal curve, on C, there is a number which tells you the degree, such that for any T in the base, the restriction of that line bundle on the to the curve that parameterized by the point T is isomorphic to the pluricanonical bundle. N. Okay, yeah, for any T. Okay, so this is the content of the original Franchetta conjecture, and this conjecture is proved only 30 years later by Haier, and also in a stronger form in 1987, Arbarello and Coronalba. They determined actually the Picard group of all the stacks MGN. Okay, these are actually generated free. Yeah, it's a free abelian group. So for your information, this is a free abelian group generated by the Hodge bundle and psi classes. So if you know what this means, so let me explain. So over a point x, c x1 to xm. So this is just a point on mg. Then over this point, you put the one-dimensional vector space, the determinant of the canonical for this is for the Hodge bundle lambda, and for the cotangent xi of c for this psi I. Okay, so these are some natural line bundles on MGN. Okay, and then later, about 2003, I think. Oops. Schroer. Oh. Oh, sorry. He proved this for any algebraically closed field of any characteristic. Okay, so the slogan of this result is that the only canonically defined line bundle up to a multiple is the canonical bundle. Yeah.
Okay, can I ask, are these stacks for you, or you could take coarse moduli schemes?
These are stacks.
But what about the famous Z mod 12 by Mumford as Picard group of M11 or something?
Yeah, I guess it's not included in this context. Because, I mean, Harris' proof is using some topological methods like mapping class group, cohomology of mapping class groups, etc. But yeah, I guess M11 is not included in this case.
You're saying it's free abelian group
For M11 as a stack?
I think that's what you're saying, or not.
No, this G is at least 2.
Sorry.
Yeah, should I proceed? Yeah, now we can ask, what about higher dimensions? How can we generalize this kind of result? So first thing I want to say is that there are some similar results for abelian varieties, some similar results on the Picard of the universal family of principally, I mean, universal family over the moduli space of principally polarized abelian variety with level structure. By Fringeli and Pirisi very recently. Then, but in this talk, I will talk about the situation for K3 surfaces in this talk. We are aiming for K3 surfaces. Okay, now let me formulate the similar question. So again, we fix a genus G at least 2. So let Fg to be the moduli stack of polarized K3 surface of genus G. This basically parameterizes things like the K3 surface and ample line bundle on that, such that the self-intersection is 2G minus 2. Okay, and let's say S to be the universal family, universal K3. Okay. Now, if you ask the same question for the Picard group, it's actually very easy. So it's easy to see by using the fact that the pick 0 is of a K3 is trivial. It's very easy to see that the Picard, the relative Picard, I will omit the pi of star, is again cyclic and generally generated by the polarization. Let's say H, okay, where H is the polarization. Okay, this is very easy because the reason, maybe I write quickly. So the reason that if you fix the line bundle on the total space, then if you restrict, so for any t in Fg, if you restrict this line bundle on this surface St, parameterized by t, then because there is no pick 0 by the degree, you immediately see that there's actually some number of the polarization, and for some n. Okay, then this is fiber-wise correct. So this is true for any t very general. because the equality can only hold over countable union of closed subvarieties. But if it's true, very general, then it's for all T. Okay. So this is a very easy argument. So the interesting is that actually to not look at line bundles, but some, you can say vector bundles, but in this talk, I will talk about zero cycles. So the non-trivial thing to look at is for zero cycles. So probably not everybody is familiar with Chow groups. Let me do a quick digression. So recall. So for a smooth projective variety X, and for any I, some integer, I will denote by Chow I of X to be the free abelian group generated by the codimension I integral subschemes. Modulo the so-called rational equivalence relation. So if you look at Chow 1, then as you can see, this is nothing but divisors. Okay, linear combinations of hypersurfaces are just divisors, and the rational equivalence relation reduced to the inlinear equivalence relation. So this is just a class group, which is isomorphic to the Picard of X. Okay, for smooth projective varieties. And the useful notation is that if I write Chow I, lower I, then I really mean Chow of cycles of dimension I. So Chow of dimension minus I, X. Okay. And the good thing about these Chow groups is that they form a graded ring. So we have an intersection product, a well-defined intersection product. For any ij, we can go from Chow I cross Chow j to Chow I plus j x. This makes this Chow star, which is the shorthand for Chow I, the direct sum. This becomes a graded ring, commutative ring. Okay, so this is called the Chow ring. So this guy, this guy is called the Chow ring of X. Okay, so already I want to mention a fundamental observation of Mumford, that Chow ring is a difficult object to study. So he observed this in 1968. So for smooth projective surface, already in surface case, the zero cycle can be complicated if the geometric genus is non-vanishing. Then this Chow 2x, or we can say zero cycles, so I put zero there, is infinite dimensional. The terminology is a bit misleading. So it's not saying that, it's not just saying that this is an infinite dimensional vector space, but it's actually infinite dimensional object. Namely, it cannot be parametrized by a scheme of finite type. So it's really like bigger than an abelian variety. Okay, so Chow 1 is of the size of abelian variety, but Chow 0 of surface with geometric genus non-vanishing is even beyond that size. Okay. So now, if we look back the Franchetta conjecture, original Franchetta conjecture, this conjecture is interesting because for a given fiber, we have certain room, certain choice for the line bundle. Okay, even if you fix the degree, there is all the line bundles of this degree are parameterized by abelian variety. Okay, you have a choice of the size of abelian variety. So the content is that actually there is a preferred line bundle on that abelian variety. Now here, for the by the Mumford observation for K3 surface, we also see that we have some room. So for a K3 surface deforming over this moduli space Fg, for a fiber we actually have a huge choice of 0 cycles. But now we have now we can ask the question whether there is a preferred point on this space of 0 cycles. Okay, so the question is that, okay, Chow 0 is huge, but is there a canonical 0 cycle? Okay, 3. So this question is successfully answered by the following theorem of Bourvil and Voisin. In 2004. So if we have a projective K3, then there exists a unique, well-defined, let me call it OS, 0 cycle of degree 1, such that it enjoys a very good property, namely, whenever you do the intersection product among 2 divisors, so here, this space is huge, but however, the image of the intersection product is always a multiple of this Bourvil-Voisin class. And secondly, some 0 cycle that you can imagine is the second Chen class of the tangent bundle. It's of degree 24, as you know, but the content of the theorem is that it's actually 24 times the Bourvil-Voisin class. Okay. So let me say a few words about this theorem. So this famous 0 cycle for Bourvil-Voisin is actually defined as any point on any rational curve containing S. So there are a lot of rational curves on K3 surface. So definitely you can define such a class. And by some Bogomolov-Mumford theorem on the rational curves in the linear systems, you can show that this is indeed well defined. And actually, the first point is also an immediate consequence of this Bogomolov-Mumford theorem on rational curves. And the second point is more subtle, but yeah, it's deduced from the so-called decomposition of the small diagram. So, okay, so this is the content of Bourvil-Voisin theorem, and this is indeed remarkable when you look at this observation of Mumford. Okay, it's a huge space. However, there is a very good canonical class in that space. Now we have the complete analogy of all the ingredients in Franchetta's original conjecture, and we can formulate the similar thing for K3 surface. This is first formulated by O'Grady. So I would call it O'Grady's generalized Franchetta conjecture. Let me just write Franchetta conjecture. He formulated this in 2013. So let me repeat the context. So, okay, we have Fg is the moduli space of genus G, K3 surface, and this is, oops, this pi, this S is the universal K3. Let me denote by St to be the fiber over T. So for any geometric point Ft in that moduli space, moduli stack actually. Now the Franchetta conjecture says exactly as in the original case for K curves. So if we take a relative 0 cycle, namely a codimension 2 cycle of the total family, then for any point of that moduli space, if I restrict this cycle Z, so Z restrict to ST, ST is the K3 surface parameterized by the point T. This guy is actually a multiple of the canonical class. I mean, the canonical 0 class in the 0 cycle class in the Chow 0 or Chow 2 actually. ST. Okay, so this is the conjecture. So the slogan is that a generically defined cycle is fiber-wise determined by its cohomology class. Okay. I mean, here just the degree. Okay, okay, now let me say some known results towards this conjecture. So let me recall the so-called Mukai model. So a Mukai model. So Mukai for generic genus G. So sorry, I have to say that for G less or equal to 10, and also 12, 13, 16, 18, and then 20. Mukai did the following thing. So for a generic genus G, K3 surface, he gives an explicit geometric description as the zero locus of some homogeneous vector bundle on some homogeneous variety. Okay, let me give you some examples. For example, if the genus is 2, then it's, as you know, it's a double cover of P2 ramified along sextic. That is an example of Mukai model. Okay, it's a explicit projective model. And for genus 3, it's a quartic surface. Genus 4, genus 4, it's a completing section of quadric and cubic in P4. And genus 5, namely degree 8, is the completing section of 3 quadrics in P5, and genus 6 is degree 10. So it's Gaussian Mukai K3 surface, namely you take a Grassmann G25, then you take the completing section of quadric and 3 hyperplane sections, yeah, etc., etc. So it's this kind of description. So he described a generic K3 surface of certain genus as such a explicit model, projective model. And using the Mukai model, the theorem of Bavik, Shen, Yin, and Yin, he proved O'Grady's, they proved O'Grady's Franchetta conjecture for those G's. Conjecture holds for those G's, okay? As you can see, as you can guess, their proof uses the Mukai model, okay? Now let me give you a very quick idea for genus 3. This is really very easy. I guess this is the original motivation for O'Grady to formulate this question.
Sorry, may I ask a question?
Yes.
In the formulation of this conjecture, so they can be any like codimension 2 cycle. So, but what if we take it to be supported over a point or fiber?
Then you restrict. So yeah, when I say restriction, it's actually the Giesing restriction, the Giesing map. So if it's supported on a fiber, then when you do this Giesing restriction, you get 0. Yeah, thanks for the question. I should have clarified that point. Yeah, I didn't put any like flatness. I just use a Giesing restriction.
I see.
Yeah.
Thanks.
No problem. Then for genus 3, you know, it's just quartic surface. Okay. It's easy to see that to show, oh, I should put genus 3. To show the Franchetta conjecture for this projection, it is enough to show it for a base change. So I base change to the, yeah, I usually denote by O for smooth. It's like all the P3, all the smooth quartic surfaces. So now we have a very nice compactification of this family. Namely, I just take all the quartics, okay? Instead of the smooth one, just take all of them. And then I have the universal quartic hypersurface, singular or not, probably highly singular at some point. And then we have an evaluation map to P3. And the key observation is that P is a projective bundle. The reason is very simple. Because what's the fiber of this P? You fix a point, then you are looking at what are the quartic surfaces passing through that point. But that just define a codimension 1 condition on this B bar. Okay, B bar is the projective space. This is just the fiber of this P is just of the projective space of 1 dimension less. Okay. Okay, then using this projective bundle formula, it's very easy to see that if you look at even the total Chow groups, yeah, if you look at their restriction to the total space, and if you restrict again on some fiber, yeah, if you look at the image, this comes always from the ambient space. This actually is generated by the H, the polarization. Okay, and that fixes the proof. Okay, that's the idea. So the key point is so the key input is the projective model, and the key point is that using this explicit projective geometry by the projective bundle formula, we can handle the cycles on the total space. In some sense, we used the degenerated K3 surface to deal with this problem. Okay, now let's move to.
So can I still ask a question about just the formulation of the conjecture? So I mean, for the original Franchetta conjecture, I mean, it implicitly gives us a description of the Picard group of the total space, right? Because it's either pullbacks or
Yeah.
And do you get something like here for Chow 2 of the?
No. Well, it's a significant. It's a strictly stronger than this conjecture, because you could have some divisors over Fg, and then you look at the universal family over that divisor, then you look at the divisor on this universal family. That also gives you a codimension cycle on S, right? So for example, if you look at some, I don't know, maybe it's called a higher Notter-Lefschetz locus of this Fg, so Picard number 2 locus, and then you have a universal K3 surface. Then on that universal K3, if you take a divisor, it will give you a codimension 2 cycle on this S. But this codimension cycle, certainly by the Giese restriction to any fiber, is 0. So this is something that cannot be grasped by this conjecture. But of course, this is an interesting question to determine the Chow 2 of this S. Did I answer your question?
Yeah, thanks.
Yeah, thank you. Now I proceed. Now the goal of the talk, or rather of the project, is to go beyond the Mukai model. Okay, how to go beyond the Mukai model. So this is actually a work in progress with Robert Laterveer.
Can I ask before you go beyond? So for the other Mukai models, it's similar arguments, but just more involved because the Mukai model are
it's basically the same argument. It's just as you said, the Mukai model becomes more and more involved. But if you are as good as them on homogeneous vector bundles or homogeneous varieties, then I think you can succeed also.
Okay, thank you.
It's a projective geometry, and some representation theory also involved here, as you can imagine. Okay, right. So now the idea is to replace the Mukai model by the associated by some associated Fano varieties of K3 type. Yeah, as you can see, the most important one is cubic fourfold. Okay, and take advantage of their and use their, I would say, rich projective geometry. Okay, if we don't have projective geometry for the K3 surface itself, then we use the projective geometry of K3 of cubic fourfolds that is closely related to the K3 surface. Okay, so I think cubic fourfolds are some kind of the common knowledge of this seminar, but let me quickly review some definitions. So if X is a cubic fourfold, X is called a cubic fourfold. X is called Hodge special. If it's an integral Hodge class, it's also the same thing as the algebraic classes, H22X. It of course contains H2, okay? H is the hyperplane class, H2 is definitely an element in this Hodge space. But if contains a rank 2 primitive saturated rank 2 sublattice. Okay, so this is the definition of Hassett in his thesis. And if the, let me change the color, if, oh, didn't succeed. If the discriminant of the lattice is D, then we say that is a Hodge special of discriminant D of discriminant D, okay? And Hassett works out that for such a lattice exists, such sublattice exists, D, so how to say, this is equivalent to D satisfies the condition star, which is the divisible by 6 or congruent to 2 modulo 6, and also is at least 8. Okay, so this is the so-called Hassett's condition for special cubic fourfold. And as we have the Torelli theorem proved by Voisin for cubic fourfolds, I will identify the moduli space and the period domain and denote by CD, the moduli space or stack space, moduli space of cubic fourfolds of discriminant D. Okay, for D satisfying star. Okay. Now, the second condition, the second definition is about the associated K3. So at some point, in some cases, for certain Ds, this orthogonal complement of KD inside H4 is Hodge isometric to certain primitive lattice of K3 surface, polarized K3 surface. So yeah, let me spell out the definition. X has an Hodge associated K3, polarized K3, XSH, if you take the KD perp inside H4 of the cubic fourfold. And on the other hand, if you take the K3 surface and you change the sign, you take the Tate twist and you take this H perp, if they are Hodge isometric. Okay. Oh, here, oh, sorry, I forgot to say that H square is D, D is 2G minus 2. Okay. Associated polarized K3. Okay. And Hassett also worked out on the Hodge theoretical level that for D satisfying star, X in CD has a Hodge associated K3. There's a Hodge associated K3 of degree D, if and only if D satisfies a further condition called admissibility, satisfies double star that, yeah, if I remember correctly, it's D over 2 not divisible by 9, or any prime that is congruent to -1 modulo 3. Okay, yeah, it's not important for this talk to understand this numerical condition, but let me just give you some examples. Okay, for the first few admissible Ds. So D admissible Ds, okay, sorry. D satisfying double stars. Okay, so So it's 14, 26, 38, 42, 62, I guess, etc., etc. But I also want to put the g here because there is always the transition of d equals to 2g minus 2. So the corresponding d is, as you can compute, is 14, yes, 20 and 22 and 30, etc. Okay. Now I can formulate also a conjecture. Usually I say this is a question, but as this is a talk, I can just be bold. But let's say Franchetta for CD, for special cubic fourfolds. Okay, so for D satisfying just star, let X be the universal cubic universal family. Do we have the analogous Franchetta property for this universal family? So for any, now the interesting cycle is, as you know, for K3 surface, the interesting cycle are zero cycles, codimension 2. But for cubic fourfolds, there is a shift. Now the interesting cycles are one cycles, namely codimension 3. So I guess if I do for any, so maybe from now on, let me write Chow groups to be Chow groups with rational coefficients. Okay. So for any relative one cycle on the total family, is it true that for any t, the parameter, the restriction of z to xt is just let's say xt is the fiber over t. The restriction of this relative one cycle to the Giesing restriction of this relative one cycle to the cubic fourfold, which is a one cycle on xt, is a multiple of some very easy one cycle that you can guess. For example, h cube. Okay, in Chow 3 xt. Okay, so this is a conjecture. Actually, this conjecture has been, I mean, this question has been verified for several Ds. But for today, I'm going to link this conjecture to the previous O'Grady's Franchetta conjecture, but for only D admissible Ds. Okay, so the starting point of our project, the starting point of the project is the following observation. Let me put it as a proposition. So let D to be admissible. So D satisfies double star. So there is associated K3. So then let me write as usual, G is equal to D over 2 plus 1. So D is equal to 2G minus 2. Then O'Grady Franchetta conjecture for this universal K3 over Fg is equivalent to the previous conjecture, the Franchetta. I mean, my Franchetta conjecture for the universal cubic over CD. Okay, so D and G are related by this numerical relation. Okay. Now let me show you again the conjecture. It says that any generically defined one cycle is a multiple of H3, H cube. Okay, so now let me show this proposition. Let me give you some idea of the proof. So let me take discriminant D, cubic fourfold. Let's say generic, just to be safe, generic. So here D satisfies double star. Now the first very important ingredient is Eddington-Thomas' work on the derived category in 2014, I think. Now, Hassett told you that, Hassett tells us that X has Hodge associated K3. And then Eddington-Thomas showed that if X is generic, then X has a so-called homologically associated K3. It's a homologically associated K3 surface S. Okay, which means that the derived category of the K3 surface is equivalent to the so-called Kuznetsov component of this cubic fourfold. I think this is really some common knowledge of this seminar, so I just give the definition very quickly. So it's 001, 02, and I think I would put it here. Yes, X1, X2. Okay, it is the admissible subcategory in the derived category of cubic fourfold. This is a K3 category, and Edin and Thomas showed that this, if X is has a hot theoretically associated K3, then it also has homologically associated K3 surface. And in fact, if you look at their proof, they actually give a K3 surface S of degree, of degree D. Of degree D. So there is a polarization comes with it. Also, what they show is that actually S is isomorphic to the moduli space of the Kuznetsov components with some Mukai vector V with respect to certain Bridgeland stability condition. So sigma is the certain stability condition on this Kuznetsov component. This component is identified by the work of Bayer, Lahos, Macri, and Sterari, and the V. And the V is the Mukai vector. So there is the well-defined notion of Mukai lattice. It's well-defined notion of Mukai lattice of this K3 category. And V is the primitive Mukai lattice, isotropic Mukai vector in that lattice. Okay, so this is the first ingredient of the proof. So I did Thomas, which provides you essentially a relation between S and X and a sheaf on their product. Okay. Now we are going to use the sheaf to produce a cycle. This is the content of the work of Boulez in 2020, I think. So he said that there exists a natural cycle Z in Chow 3 of X cross S, always with rational coefficient, such that if you look at Chow 1 of X, and the interesting part, degree 0 part, or a homologically trivial part, maybe I'd better to write homologically trivial part, then it goes to Chow 0 of S, degree 0 part, so homologically trivial by Z, and there is a cycle which induces such an isomorphism. And then by my work with Vial, also this year, maybe last year. We actually showed that, okay, we can take like, it's the third Mukai vector of the universal sheaf, universal complex. So here is the universal complex over the product. And also I think this is also contained in Boulez's paper, but what we showed is actually we give an explicit inverse where Z prime is also the third component, degree 3, codimension 3 component of the Mukai vector of the free Mukai kernel of the right adjoint of the equivalence. Yeah. So this guy is just the dual of I guess omega x shift by 4. Okay. So we have very natural correspondence between these two varieties. Okay. Then the third point.
Sorry, I think a very stupid question. The universal complex exists because you're in the untwisted case. Is that why it exists?
No, sorry, I didn't catch your question.
I was just wondering why the universal complex exists, because you're in the untwisted case, right? Is that why? Yeah,
this is untwisted in this case, but to play with the Mukai vectors, it's actually it's okay to also use twisted sheaves because you know, with rational coefficient cycles are just, all the Chen class of the twisted sheaf, you can first raise it to some power and take the nth roots.
Sure.
So for cycles with rational coefficients, you can really use twisted sheaf or untwisted sheaf by the same reasoning. There's no really something.
I see. Thanks.
Now the third point, actually, we have to use the recent work of Bayer, Lahoz, Macri, Newer, Perry, Stellani, BLM and PS. This work on the family of stability conditions and the family, the relative moduli space. So this construction allows us to show that actually this construction works in family, which is crucial because we are interested in generically defined cycles. So we have to work in families over this CD. So let me be more precise. So this, oh, sorry, there is some inaccuracy, sorry. This is not equivalent, sorry, equivalent with, this is some technical point. So the proposition is that the O'Grady Franchetta conjecture for the genus G K3 surface is equivalent to the Franchetta property for over the moduli space of a marked cubic fourfold of discriminant D. So this is actually slightly stronger than the Franchetta conjecture for universal family over CD, because the marked cubic fourfold, this moduli space is a double cover of CD if D is divisible by 6. But yeah, let me not talk too much on this point because it will be irrelevant for our main result. So this construction, okay, so let me do CD mark. And this is actually birational to this FG, okay? This is already observed in Hassett's work. So there is a universal K3 S and a universal cubic fourfold. Let me identify these two spaces. Let's just call them B. Because for Franchetta type questions, you can freely take the risky open subset. So birational equivalency is good enough. Then this S by BLM and PS, this is the relative moduli space with some stability condition of the relative family of the Kuznetsov components over this B of some Mukai vector V. Okay, then we have this diagram. Okay, so we can look at some cycles on the total family and restrict to one fiber. And also we can look at the same thing here and restrict to one fiber. Logical. And here we have this family version of Z coming from the family version of the universal sheaf. And so we have family version of Z prime as here. The explicit formula is here. Yeah. And then when restricted to fibers, they gave equivalent. They gave isomorphism. So this is Z. This is Z prime. Oh, I should put a star. Okay. So if this is clearly a commutative diagram, and this shows that actually these two conjectures are equivalent, because if you have a generically defined cycle here, namely a cycle coming from here, you restrict to here, then by this isomorphism, you can go first to here and restrict to here. But then you get a generically defined cycle on the cubic fourfold. If you assume the conjecture holds for cubic fourfolds, then you know that this image is a very easy cycle, namely a multiple of H cube. Then you push it down, you get a multiple of the Beauvais-Voisin class. So this is basically the idea of the proof of the proposition that links to Franchetta conjectures. Okay, so there are some details omitted, but I guess the idea is there. Now we are reduced to prove. Now we are reduced to prove. Sorry. Now the main concrete theorem with Laterveer is that we can prove the O'Grady Franchetta conjecture holds for a new G equals to 14. So this was not in the list of the theorem of Pavik and Shen and Yin. And by the proposition, so this is the main theorem, by proposition, we are reduced to prove the following thing. So the Franchetta conjecture for the cubic fourfold of discriminant 26, right? X pi C26. 26 marked or not is the same thing. Yeah, well, it's not, it's labeled. But the generic is the same thing. So let me just say that this is reduced to the discriminant 26 cubic fourfolds satisfies the Franchetta conjecture. Okay, let me recall you the goal. So for any 3 cycles here, the restriction of this 3 cycle to xt is a multiple of h cube in Chow of xt3 for any t in this C26. Okay, so this is the goal of the rest of my talk. Now to prove this theorem, the geometric input is here. Okay, so I said that first we use this proposition as a bridge to go from K3 surface to cubic fourfold. But what is the good of this cubic fourfold is that it has some explicit projective geometry, just as in Mukai models. So the theorem of Farkas and Vera in 2018. So a generic cubic fourfold of discriminant 26 contains a degree 7, so let's call septic 3-nodal rational scroll. So actually it contains a 2-dimensional family of septic 3-nodal rational scrolls, parametrized by the associated K3, K3S, okay, in this F14, yes. And also this is a characterization, namely, now let me put it as a remark. The remark is that any cubic fourfold, I mean, containing such a scroll is in C26. Okay? So this is a characterization. So it's a bit like Mukai model. A generic K3 is blah, blah, blah. Here is the generic cubic fourfold of discriminant 26 is a cubic fourfold that contains a septic 3-nodal rational scroll. Okay. I see that I don't have much time, so I will omit the idea of this correspondence, but really go to the proof of our main theorem here. This main theorem, okay? By using Farkas Vera result. So proof of our theorem of cubic fourfold. So now if I take a cubic fourfold in C26, let's say generic. Now we know that there is some scroll, so we take a scroll. By scroll, I just mean a septic 3-nodal scroll, rational scroll, as here. So if I take a scroll, now first step is that we vary x by fixing this scroll. So you see, we want to understand generically defined cycles on this cubic fourfold, namely cycles of this cubic fourfold that deforms on the whole family. But at least these cycles should deform along the subfamily that contains this R. So let me look at this this subfamily. So these are smooth cubics containing this R. Okay. Then it has this compactification. Yeah, let me just write it as PH0 of P5 O3 vanishing on this R. Okay, so this is, if I remember correctly, it's a P12. Yes, now just as the quartic K3 surface case that I showed you, here we have a similar picture. So we have XB, which is the pullback of C26 of X. Okay, you pull back, you get a family over this B, and then you get a compactification over B bar. Let's call this just X bar. Yeah, I don't know, X bar, B, XB bar. Okay, this is the universal thing, and it has the natural evaluation map to P5. Okay. Now, a crucial fact we are going to use is that R, the scroll, is cut out by cubics. Okay. Now, this fact implies that this, this map P, unfortunately, this is not going to be a projective bundle because, as you can see over the points in R, the fiber is the total B bar, the 12-dimensional projective space. However, over any point outside of R, by this fact, we know that it is a codimension 1 condition. So the fiber is just a P11. So P is the how to say P11 bundle over P5 minus R, but P12 bundle over P5. Oh, sorry, over R. Okay, so this is something we call a stratified projective bundle. Now, but again, by using projective bundle formula, we see that if we take the image of this subfamily, so this XB to this fiber, X, okay, it's always, oops, there are only two possibilities. I mean, this is generated by two kind of things. The first thing is that is those cycles coming from the ambient P5 to X. And the other thing is that coming from the common locus, namely R. So here, here is the pullback, and here is the push forward map. Okay. But however, we know very well about the Chow group of the P5. Okay, it's just generated by H. And for the Chow group of R, it's not complicated because R is a scroll, rational scroll. So the resolution of R is just a Hirzebruch surface. And the Chow group is generated by divisors. There are only two classes, one ample class and one ruling class. And the ample class, as you can check immediately, it's also coming from the ambient P5. So in the end, this is actually generated by the H, the hyperplane class, and the ruling. So this guy is the ruling of R. Okay. So this is a subalgebra generated by these things. Can I take a couple of more minutes?
Sure. Yeah.
Thank you. Yeah. Sorry. Now now we already obtain some serious restriction of generically defined cycles on X by using this subfamily. It's just these things. But now we start to vary R. As we see, we only use the one. As you can see, we only use the one R in this X, but in the theorem of Farkas-Vera, we have a two-dimensional family of such scrolls in this cubic. So we can also vary this R. So we vary R by fixing S. We see that the space that we are interested in, namely the generically defined cycles, this such image is in the intersection, okay, of all the R's, of all, what's happening here? Of all the R's in T. So T is actually parameterized by the K3 surface. And this is the space generated by. Now I will use LT because this is the ruling of R T, the scroll parameterized by point T. But then you can see immediately that for codimension 3, yeah, so for codimension 3, generically defined cycles, they are just spanned by They are just a yeah. Let me write Q class of H cube plus Q of this class LT. Okay, so now this is enough. We are enough to show that for any x, there exists some rational scroll RT in x such that this LT, when you look at it as a cycle in Chow 3 of x, this is actually proportional to h cube. Okay, then the intersection, then this intersection would be just h cube, because yeah. But now the idea is quite beautiful. I want to show you. So so you have a K3 surface. This is S, the K3. Okay, that parameterize all the scrolls. Then let me take some rational curve in it. I can't use the letter R, but okay, let me just call it rational curve. So all the points on the rational curve are rationally equivalent. So for example, over this point T1, I have a scroll which is singular, but let me just draw it in a naive way. And then over T2, another scroll, etc. Okay, and these LTs, these are the class LTs. Okay, they are all of the same class. Now the observation is that this class LT varies in a two-dimensional, let me call it rational equivalence orbit. Namely, this LT varies in the two-dimensional family, and its class in the Chow 3 of the cubic fourfold stays constant. Why is that? So first of all, you can, given a ruling here, you can vary it along. I mean, inside this scroll, right? Because it's rational scroll, the base is P1. You can vary along this direction. This gives you one-dimensional. But however, you can also vary the scroll itself along this rational curve. So along with this rational curve, this ruling also varies. For example, from T1 to T2, this ruling varies to deforms to this ruling. So this altogether gives you a two-dimensional deformation. So this gives you this. Now this LT, if you look at it as, change the point of view. If you look at it as a zero cycle on the final variety lines, cubic, this hyper-Kähler fourfold also moves in a two-dimensional rational orbit, rational equivalence orbit. Okay. Now by a theorem of Voisin, if we have a hyper-Kähler fourfold, which is a final variety of lines, if a certain zero cycle varies too much, namely two-dimensional at least, then this guy is simple in some sense. It's let me call this L4 to the power 4, where L is the Blücher polarization on this Fx. And then by some computation, for example, in Vial and Nijmegen's paper, we can find that, okay, then now this LT viewed as a one cycle is also in this QH3, in this one cycle cubic. Okay, so I used the same notation for the same LT. I'm sorry for that. So this finished the proof. Okay, finally we show that this LT is for certain special scroll containing the cubic, its ruling does not contribute to new classes. So in the end, this intersection is one-dimensional. So that proves the theorem. So yeah, I think the time is up. Let me just say that the same argument gives a new proof of the O'Grady's Franchetta conjecture for the genus 8 case without using the old Mukai, without using the Mukai models, but instead using the Pufafin cubics. And also it gives also a new proof for the genus 2 case without using the double plane construction, but using cubic fourfolds containing a plane. Okay. Sorry for going over time. Please ask questions if you have any. Thank you.
Okay, thanks a lot. Yeah, are there more questions?
This theorem of Voisin that you mentioned at the end, is it more general or it's specific for this?
I think she studied several cases. For example, here put the schemes of case resurface and this Bovido-Nagy variety. And in each case, she gave a certain filtration on the Chow zero of that hyper-Kähler variety. And here I say it moves too much, meaning that it's in the it's called the second step of the filtration. And she showed that the second step is actually one-dimensional. So it's not completely general, I'm afraid.
Okay.
But worked out in some interesting cases.
Okay. Thank you.
So what about D equals 26 or 38?
D equals to
26 or 38?
26 is our case.
Or D equals 38.
D equal to 38. Yes, so there is also a construction of Hoff and Stagliano, if I remember correctly, where they use Gusher-Mukai varieties. So actually, our method has some potential. I didn't say, but has some potential as long as you can relate this genus-g K3 surface to certain final variety of K3 type. For example, QB fourfolds, Gusher-Mukai varieties, the Vazan varieties, etc. And you have explicit projective geometry for that kind of Hodge special final variety. Then you have some chance to prove this conjecture in that genus. So in the in genus 20 case, you have oh, am I saying something stupid? Yes, maybe what I said is no. I didn't answer your question. It's about like a discriminant 38 Gusher-Mukai variety. But for discriminant 38 QB fourfold, I don't know. This is it's proved to be rational, right?
Yeah, and I mean they're also characterized as containing a certain rational surface by Howard Noor.
Yeah. So what is exactly the rational surface?
Some blow up of P2, maybe at 10 points. I would have to look it up.
So we actually hoped for the same approach to work for genus 22 K3 surface, namely for QB fourfold of discriminant 42. Then it's in a similar situation. It contains a special rational surface, which is a blow up of P2 at maybe 10 points. But we could not make it work yet. Because now the special surface contained there has a high Picard rank. Now we have to control many classes, not just one ruling.
Other questions?
Can I ask, so you conjecture this Franchetta conjecture for cubics with a star condition, but it also makes sense for cubics without the star condition, right? So do you conjecture it to be true also or false in that case?
Maybe you mean double star. So star is like a minimal. Otherwise, there's no CD. CD is empty. So
okay, yeah. So without the double star.
So yeah, but between star and the double star, I'm sorry. Yeah, there is called the star prime. It's the QB fourfold with twisted K3 surface associated to that, and it's also useful. For example, I said I can give a new proof. Well, I mean, we can give a new proof for the genus 2 case of the O'Grady-Franchetta conjecture. But the genus 2, there's no cubic fourfold. But of course, but actually for cubic fourfold of discriminant 8, namely containing a plane, there is there is a quadratic fibration over P2, and if you look at the relative Hilbert scheme of P1, you get a double cover of the P2 with ramified along 60, so you get a K3 surface. But it's theoretically speaking, it's a twisted K3 surface if you want to relate the Kuznetsov component of the cubic fourfold with the K3 surface. But nevertheless, as I said to Julia, the correspondence, I mean, the Boulet's argument work perfectly with twisted twisted K3 or moduli space. Then we have a direct link between the cycles on this K3 surface of genus 2 and the cubic fourfold containing a plane. So now this strategy reduces the genus 2 Franchetta conjecture to the Franchetta conjecture for D equals to 8 for cubic fourfolds over C8. But then this is very easy. You by the same argument I used, I mean, you look all the cubic fourfolds containing one plane, and then you let the plane vary. You see immediately that yeah, the one cycles in such cubic fourfolds, if it is generically defined, it's very easy. So yeah, it's I guess I find this a totally different proof, right? We never used the Mukai model. Did I answer your question? So yes, for between star and a double star, there is a double star prime, where our method could give some new proof of some old cases, and hopefully for some new cases in the future.
And we get, is it reasonable to make a Franchetta conjecture for the modular spaces of stable objects, the hyper-Kähler varieties associated to?
Yes, yes, indeed. So with Charles Vial and Robert Laterveer, we actually worked for quite some years for the so-called generalized Franchetta conjecture for hyper-Kählers. So if you fix the moduli stack of hyper-Kähler, a locally complete family of hyper-Kähler, and you look at the universal family, and you look at all the cycles that is generically defined, namely the cycles that are restrictions of the cycles of total family to one fiber, then you conjecture that if this cycle is homologically trivial, then it's rationally equal to 0. That's the content of the conjecture. And we can show that conjecture for Bovie-Donaghy family, so Fano variety lines. And also we can show recently that it holds for this Len-Len-Zorger-Feinstraten eightfold family. Because I just gave the talk on these two families 10 days ago, and I think some audience are there, so I decided to give a somehow orthogonal talk here. I'm sorry for this choice. But yeah, indeed, it's very interesting for the higher dimensional case. But again, very hard. We used the moduli space of stable objects, and your joint work with 6 people, and also projective geometry of cubic fourfolds, obviously.
Okay, any other questions? Well, if not, then let's thank Lee again.